Morning. Welcome to Krishna's class. We continue with our consideration of the Lebesgue measure and integration. We look at the so-called Vitali Caratheodory theorem. What we considered earlier was the Lucian's theorem, in which we explore the relationship between measurable functions and continuous functions. Now, in this theorem, we look at functions which are Lebesgue integrable on x, and for such a function, what the theorem says is that you can squeeze it between two functions u and v, where u is upper semi-continuous and v is lower semi-continuous. I am not saying that they are just continuous functions. You can approximate from squeeze between a upper semi-continuous function and a lower semi-continuous function, and these functions are such that their difference is integrable and their integral can be made as small as it is. So given epsilon, you can find the corresponding p and q, so that this integral is just an epsilon. Now we prove this theorem. It's also a very useful result. We assume f is greater than 1. And f is not identically does not vanish identically. So it's not the zero function. Then we know that pointwise f is the pointwise limit of an increasing sequence of simple functions. The construction of such functions we have done earlier, and we have seen that this can be done. That means we have a sequence, simple functions Sn, and f is the limit of f is the sum of simple functions Sn minus Sn minus 1, taking equal to 6. What does it say? You can approximate this function from below through a sequence of simple functions. and whose pointwise limit is the given function. Now further, what you have is the following. Suppose you define Tn equal to Sn minus 1. Then if you take the sum of now this is a Sn minus Sn, Tn is a simple function. Because it is the difference of two simple functions. Now f is equal to sigma t. Why? Because this is equal to and this is okay, which is equal to f. So sigma Tn equal to this. Therefore, f is equal to sigma Tn. Okay. Now you see that since each Tn linear combination of characteristic functions we have fx as a series made up of characteristic functions. Equal to there exists measurable functions, measurable sets ei CUT not necessarily joint and CI positive such that f of x is equal to so you can write it in the form of a infinite series of characteristic functions, scalar multiples of characteristic functions. So denote this, designate this with 2. It follows from here, this representation 2, the series converges. So you have this because so the series converges actually. Now for each EI, measurable set EI, you approximate from inside using a compact set and from outside with open sets. Okay. So there are KI, VI, VI such that so what you have is that there are compact sets KI lying inside EI and superset VI of EI. Okay. Yeah, such that measure of or minus I plus times H. the given epsilon in the theorem. Now, so what is happening is this. So you have got EI. EI you can put inside that you can choose a KI, and outside you can choose a which is open, so that the measure of Vi minus Ki times Ci is positive numbers, is less than. That means this can be made. You can choose Ki and Vi as we please, so that this particular inequality form is satisfied. That means this can be made as close to EI as possible. Okay? So that is the meaning of this statement. Okay, which is possible. Now we work with these EIs and CIs. Okay. To make the choice of B as a infinite series as given here, that is Ci times chi Vi, and that means on Vi the function takes the value Ci, but of course we have said that these EIs are not necessarily disjoint. Therefore, there could be overlaps. Okay, so you will have to sum up certain things to get the value of V at some point. Similarly, U is written as a finite sum or a linear combination of chi Ki with Ci's chosen as the coefficients, where n is chosen such that sigma infinity is less than epsilon. So this is how we choose the particular n. Having done that, now we recall our definition. See, to recall, we have defined earlier what's a lower semi-continuous function and an upper semi-continuous function. Okay. Then we observed that the chi Ki is an upper semi-continuous function. Chi Vi is a lower semi-continuous function. These two we have observed. Okay. Why Ki? What I said is chi E. If E is an open set, then this is a lower semi-continuous function. And if E is a closed set, then this is a upper semi-continuous function. is lower semi-continuous. This is what we did in our last lecture. Is lower semi-continuous if it's open. And upper semi-continuous if these close. In particular, if E is complex. Therefore, now we have the following. We find U and V. Observe that U is this follows from the relation now it is on account of this relation that we get this and the definition of well and also the definition of okay right. So you see that F is now bounded below by a upper semi-continuous function and bounded above by a lower semi-continuous function, because you see that if you look at the structure of V, what is V? V is the limit of a sequence of linear combination of chi VI's. Okay, each chi VI is lower semi-continuous. Therefore, their linear combination is also lower semi-continuous, and the limit of lower semi-continuous functions is again lower semi-continuous. Therefore, V is lower semi-continuous. Similarly, U is a linear combination of upper semi-continuous functions. Therefore, U is upper semi-continuous. Linear combination of chi Ki upper semi-continuous comma V is the limit of linear combination of lower semi-continuous functions and hence therefore U is lower semi-continuous and V is upper semi-continuous and F is squeezed between 2 and V. Okay. Now let us look at the difference of this. V minus U is equal to okay, with the definition of this, and this is less than or equal to sigma, the CA's are all non-negative, okay. So this is what it is, and four and six implies less than epsilon. Okay. So we have to use those two inequalities and then take the integral of this and find out what exactly we get here. Okay. You can show that this is actually less than. Now we take the general case. We write usual technique of writing it as the difference of two non-negative functions. Okay. Plus associated with f plus and minus b minus associated with f minus as a product. Then u is equal to you put so you can minus v2. V2 is lower semi-continuous, therefore minus V2 is upper semi-continuous. Similarly, U2 is minus U is lower now you can write this, estimate this integral, this particular integral is written in terms of u1 minus u2 and v1 minus v2 and combine them properly, and this is what you get. This is each is less than. Okay, so you can write integral over x mu b is v1 minus v2. What you can do is v1 minus u1 and v2 now what happens if you write this is less than or equal to this. Because each one is less than epsilon, this is also less than epsilon. So at is going to be set root. That completes the proof of the Vitali theorem. It's a useful theorem because you can work more comfortably with semi-continuous functions than with measurable functions. So this is a useful estimation of the f by u and v, and with the property that the difference between p and u is as small as u. So thank you very much. So we can conclude here, and from now on what we work, what we try to discuss is the so-called LP spaces. One of the important spaces that you encounter in the study of, say, partial differential equations and so on. So thank you very much.